Now we discuss hypothesis testing involving a single sample. We will examine a number of scenarios, but they have much in common. The general idea is to construct a confidence interval that is centered at the value featured in the null hypothesis, which we have been calling mu0 when testing the mean. If the appropriate test statistic falls into the rejection region that is outside this confidence interval, then we reject h0. The differences among these scenarios lie in how we obtain the margin of error in our confidence interval. What is the standard error? What distribution do we use to define the rejection region? Our first scenario involves testing the mean. We will assume that the sample size is large, and by large, I mean at least 30. This assumption allows us to use the central limit theorem, which tells us that the sampling distribution of a mean approximately follows a normal distribution. We will consider one-tailed tests, for which the null hypothesis is either h0, mu is greater than or equal to, or less than or equal to mu0, and two-tailed tests, for which the null hypothesis is mu equal to mu0. In a case where the population standard deviation sigma is known, then we use the test statistic introduced earlier, and we recall this formula for the standard error of a mean. In fact, for any of the relevant scenarios we will consider, the test statistic always has this form: the sample statistic minus the value we were testing against divided by the standard error. Look for this pattern as we move to other scenarios with their test statistics. Now let's try an example. A hatchery claims that they can grow salmon with an average weight of more than 7.6 pounds. We check a random sample of 40 fish and find that for this sample, the average weight is in fact higher, 7.8 pounds. But is this evidence strong enough to claim that this higher weight applies to the entire population of salmon in the hatchery? We will test this claim at the 5% level of significance, meaning that we will use a 95% confidence interval. Because the hatchery is making this bold claim of higher weight, we make the alternative hypothesis that the average weight is greater than 7.6, which means that the null hypothesis, the status quo, is h0, mu is less than or equal to 7.6. Then we compute the standard error of a mean from the known population standard deviation and the sample size. Next, we compute the test statistic, sample mean minus hypothesis parameter divided by the standard error. Then this value is compared to the boundary value of our rejection region, z alpha, where alpha is equal to 0.05. Because the null hypothesis is h0, mu is less than or equal to mu0, we need to check whether the test statistic z star is less than or equal to z alpha. It is, so we do not reject h0, which means there is not enough evidence to support the hatchery's claim that the average weight of the entire population is more than 7.6 pounds. So even though the sample had a greater average weight, the difference is not considered statistically significant. Now, what do we do if a population standard deviation sigma is unknown? As we did with confidence intervals, we substitute the sample standard deviation s. This is a reasonable approach because we are assuming a sample size is large, so that the sample standard deviation should be a reasonable approximation for the population standard deviation. This means the test statistic for this case is the same as before, just with s substituted for sigma. Let's work another example. We want to know if male students at a particular school can do as many push-ups now as they could 20 years ago. To that end, we take a sample of 50 students and see how many they can do. We get a sample mean of only 22.5 push-ups, compared to 24 in the past. We do not know the population standard deviation, but if we have a sample standard deviation of 3.1 push-ups, can we conclude that this decline is statistically significant? In this case, we'll perform a two-tail test. Our null hypothesis is h0, mu is equal to 24, and therefore the alternative hypothesis is h1, mu not equal to 24. We'll use a significance level of 0.05. We don't know the population standard deviation, so we use the sample standard deviation to obtain the standard error of the mean. With that, our standard error is the sample standard deviation over the square root of the sample size. Then we compute our test statistic. Again, sample parameter minus hypothesis value divided by the standard error. This is a two-tailed test, so we need to compare this to z sub alpha over 2. Specifically, we need to compare the absolute value of our test statistic to this threshold value. As it is greater, it falls within the rejection region. Our conclusion is to reject h0, meaning that the mean number of push-ups is no longer 24. How is a hypothesis test affected by the choice of a significance level alpha? As alpha increases, the value of z alpha, or z alpha over 2, decreases because the area of a rejection region is increasing. As a result, the test statistic is more likely to fall within the growing rejection region, so H0 is more likely to get rejected. The implications of this go beyond the mathematics involved. After all, if H0 is rejected, then that means there's evidence that supports accepting H1, which is generally the position that a researcher wants to establish. It follows that the researcher is more likely to get the desired result simply by choosing alpha to be large enough. Therefore, the result of a hypothesis test may be misleading, especially if important parameters like the confidence or significance level are not disclosed, and now it is clear why they should be. The bottom line is that a smaller value of alpha inspires greater confidence, both mathematically and otherwise, in the result of a hypothesis test. While on the subject of the importance of a level of significance alpha, it is helpful to have some guidance in choosing it. For this purpose, it is important to keep in mind that alpha represents the probability that H0 will be rejected, even though it is valid. This leads to the important concept of a p-value, which is defined to be the smallest level of significance at which H0 will be rejected. If we can compute the p-value of our hypothesis test, then we can simply compare it to our chosen value of alpha to determine whether H0 should be rejected. We will now determine the p-value for a one-tailed test. First, we consider the case where the null hypothesis is mu less than or equal to mu naught. So the alternative hypothesis is mu greater than mu naught. In this case, H0 should be rejected if the test statistic z star is greater than z alpha. But z alpha is the z value such that the area under the standard normal distribution curve to its right is equal to alpha. Therefore, H0 will be rejected if the probability that z is greater than z star is less than or equal to alpha, because that would mean z star is to the right of z alpha. It follows that this probability, that z is greater than z star, is the smallest level of significance at which H0 will be rejected. So that is the p-value for this test. Let's visualize the determination of a p-value. Here, z star is greater than z alpha, which implies rejection of H0. Therefore, the probability that z is greater than z star is less than the probability that z is greater than z alpha, which is alpha. On the other hand, if the probability that z is greater than z star was greater than alpha, then z star would be to the left of z alpha, which would mean that H0 would not be rejected. Now we consider a case in which the null hypothesis is H0, mu is greater than or equal to mu naught. In this case, we reject H0 if z star is less than minus z alpha. From the symmetry of a normal distribution, we know that the probability that capital Z is less than or equal to minus z alpha is equal to alpha. So by analogy of a previous case, it follows that H0 should be rejected if the probability that capital Z is less than or equal to z star is less than or equal to alpha, because this would put z star to the left of minus z alpha, which calls for rejection of H0. Therefore, this probability that capital Z is less than or equal to z star is a p-value for this test. What about a two-tailed test? In this case, H0 is to be rejected if the absolute value of z star is greater than z sub alpha over 2. Using similar reasoning as in the one-tail case, this is equivalent to the condition that H0 should be rejected if a probability that the absolute value of capital Z is greater than the absolute value of z star is less than or equal to alpha. However, because of the symmetry of a normal distribution, we can work with just the right tail probability instead of both tails, and conclude that H0 should be rejected if a probability that capital Z without the absolute value is greater than the absolute value of z star is less than or equal to alpha over 2. However, we want the p-value to be compared to the level of significance alpha, so we multiply both sides by 2 to arrive at the p-value 2 times the probability that capital Z is greater than the absolute value of z star. Here we summarize how to proceed with either a one-tailed test or a two-tailed test for the mean. Note what these tests have in common. They all use the same test statistic. The condition for not rejecting H0 mirrors the relation in the null hypothesis, and a p-value mirrors the relation in the alternative hypothesis, with a buffer of z alpha or z alpha over 2 as appropriate.